Hello. So in this video we are going to recall the concept of autocorrelation, discuss possible causes for autocorrelation, how to fix them, and how to detect autocorrelation in your regression model. So as you probably remember, under the presence of autocorrelation, the disturbance term associated with one observation is affected by the value of disturbance term in one of the previous observations. So we distinguish between positive and negative autocorrelation. Under positive autocorrelation, there is positive association between two error terms, or in other words, higher value of error term in period t is associated with the higher value of error term in period t plus 1. And under negative autocorrelation, higher value of error term in period t is associated with the lower value of error term in period t plus 1. So on this graph you can see a very bright example of positive autocorrelation. So on vertical axis here, you can find the value of the error term, and on horizontal axis we have first lag of error term, or value of error term in period t minus 1. As you can see, increase in the value of error term in period t minus 1 leads to increase in the value of error term in period t. In other words, we deal with positive autocorrelation. So what might be the reasons behind autocorrelation? First of all, some variables are lagged. In other words, change in the value of regressor in period t affects the regressand or dependent variable in period t plus 1. And in such cases, serial autocorrelation is extremely likely to occur. I will give you an example. So assume that you investigate the relationship between government spending on education and academic performance of high school students. It's very unlikely that increase in the value of government spending in period t, let's say 2020, will improve academic performance of students in the same period, t or 2020. And the reason is very trivial. This process should take some time. So with higher spending on education, schools are able to buy more computers, better textbooks, maybe some additional materials, and so on. But it will take some time until this will result in improvement in students' grades. So this process is lagged. Therefore, it makes sense to analyze the links between government spending in 2015, 2016, and 2017 maybe, and academic successes of students in 2020. But if you analyze the links between those variables for the same period, it's really likely that you will end up with autocorrelation. So you might wonder what you do in this case. First of all, you look through the relevant economic theory. Sometimes theory is very straightforward about this, and it tells you that there is some lag. You have to make some review, like look through the similar studies with econometrics and see what were the lags specified by other people. So if you wonder how you can easily design a lagged variable in Gretel, I will show you. So I'm using CPI dataset. As usual, please find it in materials for this lecture. So I click on variable, I click add lags of selected variables, and here I have to specify number of lags to create. If I click 1, then there will be value of CPI in the previous period. In our case, in the previous month. because this is a time series data set consisting of monthly observations. If I click 12, then I will get CPI, the value of CPI 1 month ago, 2 months ago, 3 months ago, up to 1 year ago. So I click, and here you have the lags of this variable. Okay, so the second reason for autocorrelation is inertia. So some economic processes are cyclical, and some of those processes are characterized by inertia. I will explain. So on this graph, you can see a very typical business cycle depiction. So time, the value of real GDP, and we know that over time real GDP increases. So this is like a general trend. It's called potential output. However, this process is not stable. So economy goes through the periods of recession, expansion, expansion, recession, and so on and so forth. So if we analyze only this period, let's say, and if we assume that this line stands for the true overall trend, potential output, then you will see that the value of error term, like the distance between your observation and some generalized trend, will be higher and higher and higher and higher and higher in the period of expansion, and then lower and lower and lower and lower in the period of recession. So this is called inertia. And if you don't believe me, you can download any data set on GDP, any GDP series. Please make sure that it's long enough. And if you make the visual depiction, okay, something like this, of this trend, you will probably see something very similar. So please keep this in mind, and please make sure to verify the data, especially when you use data on GDP for a long period of time, because it's really likely that inertia will result in autocorrelation. Seasonality. Seasonality is something very similar, but of a bit smaller scale. So on this graph, you can see quarterly, not seasonally adjusted GDP for Greece. For no apparent reason, I've chosen Greece just because it has this really nice graph. It's very easy to see. So what is the nature of seasonality in quarterly GDP? It's fact that GDP takes the highest value in the fourth quarter, just before the Christmas, and the lowest value during the first quarter, just after the Christmas. There is highest spending on consumption during the last quarter, and it's not only about consumption, it's also about business investment. So there are many reasons. The first reason is, yes, people buy a lot of Christmas presents. So that's why spending on consumption increases and GDP increases. Second, many firms close calendar year in December, and this means that they have to spend everything they planned to spend during the calendar year. And sometimes they do it during the very last quarter. So there are many reasons, but the fact is that value of GDP takes the highest value during the fourth quarter. This is called seasonality. And again, if you use data of quarterly frequency or monthly frequency, usually some initial data adjustment and transformation is required before you put your data to regression model. We are going to discuss this. Okay, so non-stationarity is a very common reason for autocorrelation in regression model. In stationary data, mean and variance of variable are constant over time, and stationarity is one of the underlying assumptions for time series data analysis. In non-stationary data, in contrast, mean and variance are not constant over time, so they change. And non-stationarity can occur because of unit root or deterministic trend. So I can give you an example. So I want to test whether CPI, Consumer Price Index, is stationary or not. So I click on CPI, I click on variable, unit root test. We are going to use augmented Dickey-Fuller test with constant and trend. Okay. So, actually have the output on this slide. So, zero hypothesis of this test says that there is a unit root. And unit root means that data is not stationary, which is bad. So in our case, we are unable to reject zero hypothesis of unit root because asymptotic p-value is either equal to 1 or very close to 1. So we deal with the unit root. The natural question you might ask is what to do. So does it mean that we have to forget about this variable? No, it does not. So the way in which you can handle unit root or non-stationarity depends on whether your data is trend-stationary or first difference stationary. So in case of trend-stationary data, series has a stable and stationary long-run trend. So in this case, non-stationarity and unit root just result from some fluctuations around this trend. But trend itself is fine. And first difference stationarity is a situation when the only way to handle non-stationarity is to take the first difference of the data. So in this case, this is the last resort, if your data is not trend-stationary, so you tried to smooth the series and still there is a problem, then try to use first difference. I will show you. Okay, so we go back to Gretel and we click on CPI, variable, filter, and we will use simple moving average filter. So in our case, number of observations in average is 12 because we analyze monthly data and we want to average up to the annual level. So I want to say smooth series. And this is the result. So red line stands for original data and blue line stands for smoothed trend. As you can see, it's indeed more smooth because red line shows more volatility. So we have this trend in blue line, and now we can check whether it actually helped. We can check whether CPI is indeed trend stationary. So we close, we click MA CPI variable, unit root test, the same specification as before. Okay, actually I have output on the next slide, and as you can see, it did not work. So even though we extracted this overall trend, still we cannot reject zero hypothesis, which states that there is a unit root. In other words, it did not help. So our next step is to take the first difference. So click CPI, add first difference of selected variables. So dCPI will stand for the difference between value of CPI in period T and in the previous period. And now again we can check unit root using the same test with the same specification. And here you have the output. So as you can see now, p-value of the test is significantly smaller than 0.05. In other words, we are finally able to reject zero hypothesis about unit root and conclude that the first difference of CPI series is finally stationary. So now you can include this variable to your regression model and not be afraid that it will result in autocorrelation problem. And our final step is detecting autocorrelation. So a bit later, we are going to discuss time series analysis in detail. That's why we are going to discuss how those tests are designed and so on. At this point, I would just like to discuss how you can interpret these tests. So first, you can use Durbin-Watson test. And in typical regression model output, you have Durbin-Watson statistics. So it's important to keep in mind that Durbin-Watson test is only for the first order autocorrelation. In other words, it can tell you whether value of error term in period t-1 affects value of error term in period t, but it will tell you nothing about whether error term in period t-5 affects error term in period t. Again, it's just about first order autocorrelation. So, Durbin-Watson statistics, ideally, if there is no autocorrelation, is equal to 2. It might be slightly higher or slightly lower. In a moment, I will show you how to assess p-value of Durbin-Watson test. So if it's higher than 2, then we deal with negative autocorrelation, and if it's lower than 2, then we deal with positive autocorrelation. So give me a moment, I will show you how to assess p-statistics of this test. Yeah, first I should run the model. So I analyze how unemployment depends on CPI. Okay, so now you can click test and Durbin-Watson p-value. So you can see that our p-value is significantly lower than 0.05. I need to use Excel in order to tell you the precise value, but it's really small. So based on this, we shall reject zero hypothesis, which says there is no autocorrelation. To be more specific, no first order autocorrelation, and we have to reject it in favor for the alternative hypothesis, which says that there is first order autocorrelation. Again, based on the Durbin-Watson statistics output, we can tell nothing about autocorrelation of higher orders. Okay, give me a second. So another option, something more sophisticated, if you want to analyze higher orders of autocorrelation, you have to click test, autocorrelation, and I want to analyze log up to 12. So I am interested in investigating whether error term a year ago or 12 periods ago affects error term in period t. So here we are. And this is Breusch-Godfrey test. Of course, there are more specifications of different tests for autocorrelation, but we are using this one because we use Gretel. So actually, using this test, you're able to analyze whether there is autocorrelation in period -1, -5, up to -12. So in our case, it's present in period -5, -2, and -1. So actually, you see, it's really helpful to analyze higher orders of autocorrelation, because sometimes Durbin-Watson might not be enough. There might be no first order autocorrelation, like this one, but there might be autocorrelation of higher order. So yes, and again, based on p-value, we can reject zero hypothesis about the absence of autocorrelation. So as I told you, during one of the next lectures, we are going to analyze time series analysis in detail, and I will tell you more about autocorrelation and models which are designed specifically for for processes when autocorrelation is unavoidable. In next video, we are going to discuss the problem of heteroscedasticity, how to indicate it and how to deal with it. And I really hope you enjoyed this one. So see you.